Hi, my name is Victor, and today I want to talk to you about hydrogen storage in aviation. As we all know, the aviation industry needs to make changes in order to meet the international sustainability goals. And as you might know, hydrogen is one of the potential solutions, but there is a lot of challenges that need to be tackled before it can be adopted as a fuel. In aviation, we like to talk about weight, as we need to keep this at a minimum to reduce the fuel consumption. But hydrogen is actually quite a good energy carrier, as its energy density per unit of weight is 3 times higher than that of traditional aviation fuel. The problem, on the other hand, is volumetric energy density. In fact, to store the same amount of energy, one needs 4 times the volume. This leads to the strange designs you might have seen, with the large tanks on the top of the fuselage, which makes the airplane look like a beluga, or narrow walkways in the front of the cabin. And I don't know about you, but I don't think many passengers would want to board such an aircraft, and thus not many operators will want to buy it, which is not desired for the manufacturers. The goal is thus to maximize the density of the fuel such that these negative effects are minimized. When looking at the density of hydrogen as a function of pressure and temperature, one can see that there are many different combinations one could store the fuel at, where one can even choose the phase of the fuel. Unfortunately, it's not as easy as simply fixing the properties of the fuel, as the storage variables will actually vary during the mission of the aircraft, when we need to take into account both the filling as well as the draining of the fuel tank. Therefore, we need a thermodynamic model which enables us to give as inputs the design of the storage system, the initial properties of the fuel, and the mission of the aircraft, and gives us as outputs the volumetric and gravimetric efficiencies of the system, such that we can evaluate the performance of our design, and provides the thermomechanical loading of the storage vessel, which in a later stage will aid in the design of the fuel tank. Which, as you might imagine, will not look like a traditional one, where the fuel is simply stored within the wing box, but more like a pressure vessel, and thus have a round-like shape to cope with the pressure difference. However, we will still like to have the highly integrated structure to make efficient use of the available load carrying capability. Therefore, with analytical and numerical models, I want to see how we can subject the body of the storage vessel to external loads, all while taking into account that the vessel needs to be closed, thus accounting for the strain compatibility at the transition between the body and the end caps of the fuel tank. And maybe we can even play with a composite laminate, such that we can deviate from the traditional circular shape, such that we can make more efficient use of the available volume. Thus, what I'm working on in my PhD is quantifying the thermomechanical loading of the storage vessel originating from the stored hydrogen, and examine how we can make use of the storage vessel as a primary structure, while keeping into account that the external loads need to be introduced into the structure. With this, we will be able to support the design of efficient, safe, and well-looking aircraft that passengers will want to board and thus operators will want to buy, all the while making the aviation industry a little bit more sustainable.